All right. Right. We are gonna continue in on the ocean energy, specifically ocean thermal energy. Okay. So last time we talked about the first configuration, which is the open ocean thermal energy conversion. OTEC stands for ocean thermal energy conversion, and it's open because he take the warm water from the surface. So we will let water in our cycle, and the cycle is open for that water. So later we will see a closed system where that water never mix with our cycle. So in the open, we took the water and we flash it by reducing the pressure. We got some vapor, some liquid. The vapor go to the turbine, the liquid, because now it's at lower pressure because we just flash it, that need to have a pump over here. There has to be a pump that will take it back to the ocean, right? And the steam will continue, expand, and then once it expands, we have to condense to make it liquid again. Why do we condense? Because once it's liquid, it's easy to pump again with another pump to throw it away into the surface. Okay, so obviously the stuff that you're sending from here and the stuff that you're sending here need to be away from the warm intake. So we need to always get warm intake, and whatever we are throwing, whether it's really cold or a little bit cold, need to be thrown away from us, right? A little bit far away. And so we did this example, and you guys had a homework about doing those calculations at different pressure or even different configuration. And I just want to say that how this design is really cool in something, and that is the water that you're sending from here is actually clean water, right? Sorry, not this one, this one. This one that you're sending over here is clean water, meaning it's not salty water. See, this one, when we flash it, that vapor come, but then this is just a little bit even more salty. Why? Because we took some vapor from it. But the rest that went through the turbine and expanded, that is clean water. So people can drink it, right? So if this was a station sitting across the ocean or across the beach from a place where they don't have fresh water, like in the Middle East or something, they can actually drink that water. So they got energy and they got water, and that water could be more expensive than the energy, right? Because they spend a lot of energy to turn the seawater into fresh water. So if you're gonna give it to them for free, they will be paying for it, right? To make a system like this. Very good. So now let's talk about the closed OTEC. So why it's closed? Because the Rankine cycle that's running over here between the boiler, turbine, condenser, and pump, that is a closed cycle. And this is actually allow you to have a lot of flexibility in what kind of fluid is running here. It doesn't have to be steam. As long as that fluid boil here and he make vapor, whatever that vapor is, propane vapor, methane vapor, butane vapor, any fuel, any fluid that can be vapor, he can go to a turbine, expand, we condense it, pump it, and the cycle continue, a pure Rankine cycle. And that boiler is being run by the hot surface water, and that condenser is being cooled by the deep cold water. Okay, and we have seen this cycle before, right? Where in geothermal, we used to call it what? We used to call it binary cycle. Binary because there was two fluid. One that's the guy that's going inside, maybe ammonia, and the guy that's outside, which was used to be the hot underground water that's coming for you. Well, now we are pulling it from the surface, right? It's not as hot as the ground water, but it could be 27 degree, 25 degree. Of course, anytime you use a heat exchanger, you expect delta T between the hot and the cold. The water that's trying to heat the fluid that's going into the Rankine cycle, they have a big, not a big, but they have a delta T between them. And so to start with, we already have a small temperature difference to work with in the first place between the surface hot water and the deep cold water. The difference was not that big. So now with two heat exchanger, and they have to be closed heat exchanger, not direct contact heat exchanger like the one we saw before, or the flash chamber. So now with closed heat exchanger in both of them, you have this big, not big, you have this temperature difference between the surface and the deep ocean. With the heat exchanger in both of them, your delta T is even smaller. So your Rankine cycle is working over a smaller temperature difference, which then would result in smaller efficiency, which mean for considerable megawatt or kilowatt output here, you will have huge flow rate. Why? Because your efficiency is very small, right? But anyway, he's making the point that, you can use very exotic fluid, anything that you can dream of, you can try it as long as it boil here and it condense here. Of course, you know that, well, the boiling is not a problem. I can make the fluid boil at any temperature I want, if not any, but a lot of temperature. He can boil at a lot of temperature if I have the right pressure, right? So it may end up being have to be very high pressure so that he would boil at not really that high temperature, right? And this guy could actually be at also, depending on the fluid that we are thinking of using. So here is a paper, research paper from a group in China. They were actually saying, well, let's make a small ocean thermal energy conversion where it's a closed loop. And now since it's a closed loop, in our condenser and in our boiler, we can, that cycle here, we can try anything we want. And they tried a lot of working fluid. You can see all the refrigerants, fuels, ammonia. And they saw what happened to the efficiency if you try those different fluids as function of the inlet turbine pressure. So they can play with the pressure and they can play with the fluid, and they can see how does efficiency go. And you can see you can hit like say 5% or something over here. So it gives you flexibility for sure, right? And so this is here I'm telling you, well, that heat exchanger then has to handle a lot of heat transfer because the efficiency is very small. We need Q. So if the work net that we're going to get, the kilowatt hour or the power that we are going to get from this power plant is the efficiency multiplied by the Q input. And the efficiency is maximum 5%. So that means that to get a decent work net, you have to have huge Q added. And where is the Q added coming from? It's coming from the heat exchanger that will use the seawater to heat our ammonia, protein, butane, propane, whatever. So we need a big heat exchanger, right? We need to know what's the calculation for that heat exchanger. So the one and only equation in heat transfer that everyone should remember after a heat transfer course is Q is UA delta T. UA delta T. A is the area, the surface area of the heat exchanger, which is if that heat exchanger is like this picture over here, bunch of pipes, then that area would be the area of one pipe by not the cross-section area, because that's a common mistake people do. It's not by over 40 square, it's the heat transfer area. It's by dl, multiplied by the total number of pipes, right? By dl multiplied by the number of pipes. Circumference, length, number of pipes, okay? That's the area. And U, what is U? That's the overall heat transfer coefficient. Okay, the equation is this. You probably have remember this from heat transfer or from thermal fluid design course. 1 over UA is 1 over H I area I, the heat transfer on the inside of the pipe by convection, R conduction, plus 1 over H out area out, the heat transfer on the outside. Those are the three resistance in series that the heat transfer need to cross. Maybe condensation or boiling from the outside, conduction in the pipe, and convection on the inside. And where do we get those H? One guy was asking me last week about how do we get the H of the swimming pool for our project. You know, when the air is moving around and we are trying to calculate the convective heat transfer loss, where do we get this H? Where do we get the H for the flow in a pipe? Where do we get the H for boiling on the outside of the pipe? We get it from the heat transfer book. The heat transfer book, which I have over here, right? Isn't this our heat transfer book that we had in this university? So you open that book and there are chapters, you know, for every one of those things, right? There are chapters for natural convection. There are chapter 7 is external force convection. That's the swimming pool if you have external force convection. You have wind and it's flowing on the thingy. Internal force convection, that is if I would like to get this H inside, I will use the internal force convection, right? And if I want to get the heat transfer coefficient on the outside of the pipe, because it's boiling, I will go to chapter 10, boiling and condensation, right? So each one of those configuration or flow regime, you know, whether it's force convection or internal convection, or they have formulas for them depending on, say, the Reynolds number, how quickly the flow is moving. It'll tell you in this range, use this. In this range, use this. Also, it could be different for different geometry. So natural convection, for example, if it's a hot plate facing up, that's one heat transfer. If it's a hot plate facing down, that's another equation, right? But that's what this book is for all those formulas. And usually the H doesn't come like H, it's usually part of a Nusselt number, which is H length scale and divided by a K, some kind of conductivity, right? So anyway, once we get those H's and our conduction for a pipe, you will be able to add and say this three of them together is 1 over UA. And I'm saying here UA, they are either based on the inlet area or the outlet area. Okay, so if you are using the outlet area, that would be U outlet area. If it's on the inlet area, the U will be based on the inlet area. It doesn't really matter. You use them as a team. UA, you get them. Actually, you just need those two guys together because in the equation, they are together, UA. So it doesn't matter whether it's area inlet or area outlet, as long as the U is with it. Or basically, it's like those guys, all right, together. Very good. The point is, Q is UA delta T. So now with a small delta T, you can see how the area has to be really big. And why the delta T is small? Because if we make delta T bigger to save on our heat exchanger area, because we don't want our heat exchanger to be huge, then there will be nothing left for the Rankine cycle, right? So the Rankine cycle running between this temperature and this temperature, if you squeeze this even more because you want to get your heat exchanger big delta T, the Rankine cycle will be running over a very tiny delta T. It would be really not practical, right? So a compromise has to be made because you cannot give the heat exchanger big delta T and leave the Rankine cycle with nothing to work between, right? So the delta T of the heat exchanger, by the way, how we can calculate this. I'm saying this because if boiling is happening on the outside, that propane or butane or whatever is working on that cycle is boiling, he would be boiling at he could be boiling at constant temperature, right? Or say the condensation over here right, in the condenser. That fluid, again, is going to condense at constant temperature, while the cold water coming from deep under is going to do this. So the question is, what is the delta T? The delta T in this equation is T hot minus T cold, say in the condenser. So is it this one or this one? Is it delta T at the inlet or delta T at the exit? Which one is it? You probably think T average, and you wouldn't be wrong that much. You're slightly wrong. So delta T average, meaning that let's have this and this, add them together, divide over 2. So that mathematical average would work if the difference between this and this is nothing, or very small. And that is the case in this application, because to start with, they are not really big deal, right? But if there is a huge difference between T inlet and T outlet, or delta T and delta T, mathematical average wouldn't work. It would reduce error. So what do people do? They use something called, if you remember, from heat transfer and thermal fluid, we use logarithmic mean temperature difference. So it's a way to get a good delta T, that there is a mathematical proof why this is the best delta T to calculate the Q, rather than mathematical average. This formula will become the mathematical average if the difference between the two of them is not that big. So if the difference is not big, mathematical average would work and produce almost the same results as this formula. So what does this formula say? It say that here's your delta T at the exit, here's your delta T at the inlet. Your actual delta T should be delta T2 minus delta T1 over ln delta T2 minus divided by delta T1. So ln the division, and on top you have delta T2 minus delta T1. And amazingly, or like luckily, it doesn't really matter who is delta T2 and who's delta T1. The inlet and the outlet, you would think that has to be delta T1 is the inlet, delta T2 is the outlet. Sure, but it doesn't really matter. Why? Because if you flip this, you'll also flip this, and ln 1 over x is minus ln x. So whether you're going to say 7 minus 5 divided by ln 7 over 5, it's exactly the same as 5 minus 7 divided by ln 5 minus 7. But I would go with the big one minus the small one, because I don't want to have negative and divide over negative. Why? I would do the bigger number minus the smaller number. Whether the bigger number is here or here. I just go to the two ends, get my delta T and my delta T, and the bigger one, I'm going to subtract it from this and divide over ln the difference, right? So now this formula, Q is UA delta T, with delta T calculated like this, that is accurate for parallel or counterflow. Parallel, what's parallel? We come from the same place, we leave to the same place. Counterflow is we are doing this. The hot fluid is coming here, the cold fluid is coming here, and they go like this. This is actually better configuration. Of course, counterflow is always best than parallel, because it allows you to do what? To get the cold fluid as hot as it can, and the hot fluid to get as cold as it can. This is really great. If all your if what you care about is bringing very hot fluid to cool it down quickly, or like a lot, that's the way to do it. But in parallel configuration, you are pushing them against each other. And so this guy cannot get any colder, this guy cannot get any colder. So you are basically fighting yourself in this parallel configuration, right? Of course, when it comes to boiling and condensation, you think it doesn't really matter, because one of the fluids are boiling or condensing, which means constant temperature. So whether I'm going to go from the right or going to go to the left, the other guy everywhere is sitting at one temperature. If this is the case, then it doesn't matter. But most of the time, there is also, before he do the constant temperature phase change, there is a previous part or an earlier part where he is approaching the T saturation. So he's coming from here. Or if this was a boiler, he will start cold and then start boiling. So it's never really the case where you are just constant temperature throughout. There is a small part that has sensible heating, meaning that he's either dropping his temperature or going up after he finished boiling, and he's now going to be super heated. So if you have sensible heating either before or after the phase change, again, counterflow is more beneficial to you. So always use counterflow when you have a chance. Don't do barrel flow. But the point I want to make too is that this formula is only correct for barrel and counterflow. Whether you like barrel or not, but this formula is correct for it. But if I do other configuration, like for example, shell and tube, why would I do shell and tube? Because it's so compact. You can pack a lot of surface area in such a small thing. Or cross flow, like your radiator in the car, where the radiator is sitting like this, the wind is going this way, and the air is coming, the fluid is coming this way in your radiator, and you would go like this, but the wind or the air is going normal to it. That's a cross flow. All those configuration, and they exist in the heat transfer book. They will tell you that you cannot use UA multiplied by the logarithmic mean temperature difference. Why? Because the delta T is not exactly this. The delta T is going to be a little bit smaller than this. Okay, by how much? By a correction factor F. And you get that F from the charts in the book. And there's a chart for every one of this configuration. So for example, like look at this one. The tube side is doing that while the shell side is doing this. So this is almost like, when you think about it, counterflow, like this guy's going this way, this guy going this way, except that that hot fluid is meeting the hot fluid inlet is meeting the cold fluid out. That's great. That's the way counterflow should work. But then immediately he's meeting the inlet flow, the cold flow inlet, which is the coldest temperature. Why would I put the largest, hottest temperature next to the coldest temperature ever? That changed the delta T between this and between this. It changed this. It's not pure counterflow anymore. And that change in the delta T make you have to depend on experiments to come up with a correct correction factor for it. And that's why those charts exist for. Okay. Very good. So we can follow, we can use this chart, we get the F, and it's usually less than 1. It is always less than 1. And it's kind of penalty that tell you, oh, you think your delta T is 10 degree? No, it's 10 degree multiplied by 0.85. So you lose 15% because of your configuration, because it's not pure counterflow, all right? Okay, so that Q is UAF delta T. It also happened to be our Q useful. It happened to be the Q that we send to our fluid, the working fluid that's going in the Rankine cycle. And so it's going to be M dot CB delta T. And that's how you'll be able to get his delta T, for example. Okay, or M dot. So those charts will look something like this. You probably should remember them from the heat transfer book. And the chart has the F on the y-axis. So I need to come and read and tell myself, my F is 0.7. For example, how do I read? I need to know which curve. I need to know my x-axis. If you open this, you will see that the x-axis is written in small temperature and capital temperature. What is those? You look at the chart key and he will tell you. The pipe side, this is TI, T out. The shell side, capital TI, capital T out. So you follow the recipe, you find out what is your P, you find out what's your R, and you go and read, and you get the F. Okay? But you make sure you're using the right chart. If it's like one shell, and multiple tube paths or 2 shells. Sometimes they put them in 2 shells, right? So you just use the right recipe and you'll be able to get it. Cross flow, okay, and the cross flow, if you look at the drawing, they have those baffles, and here they have only one baffle and the other one doesn't. What does that mean? Does anyone remember? What does it mean that you had this division in both flows, and this one you have only one divided? That has to do with what? With fluid being mixed or unmixed. Fluid being unmixed, meaning that he's going in separate passes, like you go to a radiator and you find that the air going into between baffles, right? So they don't mix with each other. The air go, and every amount of air going and cooling its own section, right? So that would be both fluids unmixed. Both fluids unmixed. This one fluid is mixed and the other one is unmixed. Okay, so which one is unmixed? The capital T. So if in the problem statement he say, I have this heat exchanger and one of the fluid is unmixed and he come at 50 and he leave at 40, while the mixed fluid, this is the mixed fluid. This is unmixed. Unmixed mean that we divide him. We send him in separate passages. That's why he's unmixed. So he would say the unmixed fluid is coming at 40 and he's leaving at 30, while the mixed fluid, he just come as a whole, is coming at this temperature and this temperature. So you would know what is the capital T from the problem statement, from the description, right? Very good. Same thing. So you just follow the recipe, P and R. R is the curves, P is the x-axis, and you'll be able to tell what's here. And you can see the best case scenario is 1. The best case scenario is like you are approaching counterflow. And the worst case scenario is like you are really there, where you have big penalty for your delta T. So if you get this problem in the final, that would be your lucky day. And it came 1 year. Why it's lucky day? Because that is like a simple Rankine cycle. And I mean, you can ask about the efficiency, for example, or you can ask about the how much m dot is needed to generate 100 kilowatt of energy, which is still related to efficiency. You need to calculate the efficiency so that you would say Q input is the work net divided by the efficiency, right? Or you can ask about how much m dot warm air needed, or how much m dot cold, how much m dot warm water is needed, how much m dot cold water is needed, like how quickly you need to put water from the ocean to cool the condenser. And those are simply just first law thermodynamics. And if you ask about the area of the heat exchanger, how large the heat exchanger area should be, that is those equation. Q is UA delta T, like this. So it's a really simple problem. What complicates the problem sometimes is because of the exotic fluid that they use, it's not water, you have hard time getting the property. And so when I gave this problem last time, I didn't want the student to spend time trying to find the property. So I basically give them this property in the problem statement. So then they spend all the time really doing the analysis rather than what is the H, what's the H, what's the H, right? So when you look at this problem, he said propane, and it's boiling at 22 and condensing at 11. 22 and condensing at 11. So big delta T? No, very small delta T. Just 11-degree difference. So I mean, if we not cheat, but if we go and look at the efficiency, you'll find out it's not really going to be that big, right? Because of the small delta T, right? Let's jump and see the efficiency together. How much? 3%. right? Surprised? No, I'm not surprised. I mean, what can you do with 11th degree? You do 3%. That's what you can do, right? Okay, so he want out of this turbine, he want 125 megawatt. That's a lot, 125 megawatt. So it's probably he's gonna suck a lot of water out of the ocean. And so he said, determine the propane flow rate. You need to know how much m dot is going through this, and then determine the warm and cold water flow rates. You need to know how much m dot water and how much m dot cold water is coming. Okay. And the ocean warm water from the surface is coming at 28, leaving at 25, and the ocean cold water from deep, it's coming at 5 and leaving at 8. Okay, why do we get those temperature? Why do we need those temperature? Because that's the way you can calculate the m dot cold water. If you figure out how much is the heat transfer needed for that condenser, that Q that's leaving the condenser is going to be absorbed by the m dot cold water, which make that Q equal to m dot Cb delta T, right? M dot Cb delta T. That is the Q going through the heat exchanger, which happen to be the condenser. And the same thing for the boiler. I mean, that boiler is also a heat exchanger. And while that boiler need to boil propane, it's cooling the warm water of the surface. The surface warm water is being cooled by that propane boiling, right? It's cooling itself from 28 to 25. So if I want to get this m dot, what I'm going to do, I will have to find this Q and say that Q is equal to m dot Cb delta T of the warm water, right? So both problem or both flow rate will come just from the first law of thermodynamics. M dot Cb delta T is equal to that Q, M dot Cb delta T is equal to that Q. So then we need to tell ourselves, I need to know what is this Q, and I need to know this Q. Q condenser, Q boiler. To do what? To run this cycle, right? And this cycle is supposed to make propane here. He said the propane is, let's read. Oh, the cold water, the condensing at 11. Plant is 125, turbine efficiency is 0.9. That's the isentropic efficiency of the turbine. The overall heat transfer coefficient for both the evaporator and the condenser is 1400 watt per meter squared. That's the U. Determine the propane flow rate, the evaporator, condenser surface area, and the flow rate. So we know the flow rate, we know the power required, we know the efficiency, and we know the U. And the U is important for the heat transfer equation. Q is UA delta T, logarithmic mean temperature difference, kind of T. So let's start with getting m dot propane. How do I get that? He asked it to generate 125 over here. So how is this 125 will get generated? M dot delta H, H1 minus H2 will be equal to the 125. So if I know this H and I know this H, I'll be able to say m dot delta H equal to the output, which is 125. Of course, there's the pump work, but throughout this book, you have seen that he would neglect the pump work compared to the turbine. Of course, the more accurate way is to calculate the pump work, right? But he is right in thinking that it's really tiny in those systems. And so you have permission in this course and in the final to say, but you have to say it. You have to say neglecting pump work, work net equal work turbine. And then you will be okay to not to calculate what happened between 3 and 4. Okay, just like our textbook is doing. Again, it's more accurate to do it, but it's really small, so that's why. So So I need this H and this H. How do I get my H? So again, this table provided in this problem, or at least in the exam, it will be provided. At 22, I come here and I get HF and HG. This is HF and this is HG, right? So I'm going to use that HG. It's going to be 918. And then I need H2. How do I get H2? We did this so many times. First, we need to get 2S. How can I get H2S? What H2S? Same entropy. So I need this S, and then I come here and say it's the same S, right? How do I get S at 1? S, F or SG? SG. At 22 degrees, it's SG, 5.6. So I got myself SG. And then I'm going to say S to S is the same as S1, which is SG at 22. Okay, I got my entropy. Then what? Remember, we are trying to get the H. But the only thing I know about this point right now is the entropy and the temperature. It's 11, and its entropy is the same as this one. So what do I do next? I get the quality, X to S. How do I get the quality? I would say S to S minus, or S to S is equal to SF at 11 plus X2 times SFG. S at G minus S and F. So what I'm saying is that S to S, which is the same as S1, 5.6, 5.6 to 1 is equal to 4.3, that's SF at 11, plus X to S times this guy, SFG. And that allows you to calculate the entropy over here. That allows you to calculate the quality over here, X to S. Once you know the quality, you know your quality is 0.8 or 0.7, you can calculate the H the same way we calculated the entropy. And we did this so many times, right? So what will be H to S? It's going to be HF plus X to S times HFG, which is HG minus HF. And you got this way, you can get your entropy. So now you got your entropy. So you have now H1 and you have H2S. You can calculate ideal work, which is H1 minus H2S. You divide over eta turbine, the 0.9, and you get yourself the actual work, which is H1 minus H2. And that's what you see in his solution over here. Okay, so he's trying to get the entropy here. Then he will go and get the quality over here. Then he use the formula to calculate the H over here. Then he calculate the ideal work, right? And be careful, that book sometimes make number mistakes, just math mistakes. So, but I guess this time he did it right. 918, right? 918, that's correct. Minus 904, which he just calculated. That's the work ideal. And then he multiply by eta turbine, he calculate the work actual, which will be a little bit smaller. Okay. And then he tell himself, well, what's my m dot propane? It's the power that you want, 125 over work actual. Right? Of course, you know, if we want to really be accurate, we should have also some kind of generator efficiency, right? We need to have a generator efficiency so that it would eat a little bit more too. But usually they are very high efficiency machines, so they don't really have that much drop over. Good. So now let's calculate this m dot motor. How do we do this? We need to know the Q evaporator, the Q evaporator or boiler, and say it's going to be m dot CB delta T. So he's calculating that Q evaporator, right? And he's saying it's the H over here, the 918 over here, minus this H. Okay, and so this H is not exactly that H, but it's pretty close. Because what? Because the pump work is very little. So H4 and H3 is very close, and H3 is is what? It's HF is 546, right? 546. So you can see 546. So you're basically thinking, well, the boiler or the evaporator, can call it both thing because it's making its job is to make vapor anyway. So it's this guy minus this guy. He got himself Q evaporator. Okay, so m dot delta H. Now this is being carried out by the warm water. So if you want to calculate m dot warm water, you would say that Q, and you can see how big it is. For 125 megawatt, he's pulling 3 megawatt. For 125 megawatt electricity, he need to pull how much heat? 3 megawatt. Why? Efficiency, we have a spoiler alert, right? The efficiency is 3%. That's why. So you need to think, I need 30 times more. For 3% efficiency, you need 30 times more heat than what you're going to produce. Right? So we can use this to calculate m dot. We can also use it to figure out what's the area of the heat exchanger. Because the Q, those 3 megawatt, is UA delta T. UA delta T. All right? And again, what delta T we should use? Delta T logarithmic. This minus this. Okay, so now notice that the warm water is coming at 28 and leaving at 25. 28 and 25. The propane is coming at almost 11, right? And then boiling to 22, and then keep boiling at 22. But when you look at this calculation, he thinks that the propane come at 22 and leave at 22. He is neglecting this part. He's neglecting the sensible part. See, when he's calculating the temperature difference, delta T2 and delta T1, this and this is all based on 28 minus 22, 25 minus 22. So why he's doing this? Of course, this is not super accurate. An accurate way is to design this in 2 phases. You design this part and then this part, and you calculate the area for this part and for this part. That's not that hard to do. It just requires you to calculate this temperature here so that you would do this part. And to calculate this temperature here, you need to know this Q and compare it with that Q, then you'll be able to figure this much, right? But anyway, the reason why he could be justified in doing this is that that sensible part does not take that much energy and the fluid will go up very quickly. And also, he is kind of like, if you want to approximate the solution or the design, you approximate it on the safe side, right? So you don't approximate, I mean, you don't say, well, I think this building can take, I don't know how many level, but I think it's supposed to be designed only on 2 level. And then you get surprised, it's 20 level. No, you feel on the most conservative way, you would say, well, that's, for example, the city doesn't allow anything bigger than 20 floor. I'm going to design over 20 floor. Bad example, but you got the idea that you want to make safe assumption. So by he saying that I think the delta T is only this much rather than this big delta T, he is over designing his surface area. He will end up calculating bigger surface area. So if it turns out the delta T is really big, that condenser will be very comfortable, or that evaporator will have very big area for him, or it will do the job. It's not gonna come short, right? But again, if you have the time, you would do it this part and this part alone. If you don't have the time, you design over a safe range rather than. So this big delta T, this is liability in the design, right? You think I have so big delta T, and then you basically find out that you don't have enough surface area. So as I told you earlier, I think One of my friends, he actually worked for a big bus company that design and construct buses, and specifically HVAC equipment for big buses. And so the customer would say, come and say, well, design the heat exchanger for this small delta T. Again, they want to make sure that the heat exchanger is really big so that even if you run with this small delta T, it will work. And you will tell them this is too conservative. Like we really have a little bit bigger delta T. We don't have to have all that heat exchanger on top of the roof of the bus. We can make it smaller because a realistic delta T is actually this, not this. The same idea, right? Very good. So now we have the logarithmic mean temperature difference. We have the U it was given. We have the Q dot. We calculated from the propane. We can calculate the area. You can see he's calculating the area and it's huge. Why huge? Because the temperature difference is small, 4 degrees. Again, he's just letting the heat exchanger run over 4 degrees. So, but if you make it bigger, yes, the area will drop. I mean, imagine if it's like 8, that area will drop by a factor of 2. That's a big deal. Right? Half the area, going from 4 to 8. But if you go from 4 to 8 and you double, you make this area half, you will end up with not that much for the propane. So the propane will run rather from 1122. If you take 4 degrees from him, he will run from what? From 11 to 18. So he's running over 7 degrees. That's very little, right? But I would say maybe this is a good, there's a compromise over here. This is a screaming for a design problem. How we design a system like this so that we can maximize efficiency of the propane and minimize the area of the heat exchanger. And so depending on which one is more expensive. Right? And you can see how he's calculating m dot warm water by saying q dot m dot delta H. The q dot that's going to the warm water is m dot delta H, which happen to be, you can do it two ways. You can do it m dot CB delta T, right? Or you can do it from the steam table. So that warm water, if you give the steam table its temperature and you treat it as compressed liquid, what's a compressed liquid? It's this part. I'm not referring to propane. I'm referring, if this was a TS diagram of water, the compressed liquid part would be this side, right? And so what they usually do is that if you say I have 22, it doesn't matter how high pressure is, they just give you the H saturated. So they think the H is only function of temperature, not of pressure. And that's a good approximation, right? So either way, so whether you have a detailed compressed liquid table that you give him the pressure and temperature, and he give you the enthalpy, or you just give him the temperature and he give you the HF, the saturated liquid enthalpy, at that temperature, that works too. And its number are very close, very, very close. Cannot emphasize how close it is. It's a really good approximation that the H is of compressed liquid is only H of temperature. It's a very, very good approximation. Okay, so you calculate m dot water. You can see how big it is too, right? And so we can do the same thing on the condenser side, right? So you calculate the delta T on the condenser side. This time it's a little bit easier because 11 minus 5 and 11 minus 3. Sorry, 11 minus 5, 11 minus 8. So 11 minus 5, 11 minus 8. The temperature difference at this side and this side. And so it's 4.3. And you use Q as UA delta T. Again, delta T is logarithmic mean temperature difference. Right? And you'll be able to calculate the area, huge area. And you calculate m dot cold water, how Q dot condenser, the Q that you're pulling from the propane is m dot delta H over here. So really huge m dot, okay, and huge area. And finally, the efficiency is power output over power input, which is Q evaporator, and it's 3%. And he's making the point that those closed systems require huge area. At least the open system didn't have this area, right? The open system basically have just like a flash chamber where you generate the vapor, and then you can have direct contact condenser, which the surface area come from all the droplet that he spray. Remember, he spray water and the vapor condense on the water. So he's saying we need to reduce that area in the heat exchanger, both of them. How do we do this? Because otherwise that would be a huge plant with helicopter and stuff to generate 100 megawatt. You just have to build a huge place. Interesting, you see how the warm water is coming in, right? And how the cold water is coming from deep inside. Okay, and once you get that cold water for the condenser and the hot water for the boiler, you reject both of them here. But you make sure you reject them in a place where you're not pulling them back, right? Don't short circuit yourself, basically. That's what I'm saying. So cold water discharge and warm water discharge. Okay, so how can we shrink the area of something like this? Especially that this area is not just the size, it's also the money. Because if we only use those compact heat exchanger, those are like made for corrugated sheets. Those you can put a lot of them in such a small place. For those people who went to the tour in that was organized by the SME to go into Iran, and they had all those like compact heat exchanger. You know, they are so impressive how they can fit so much surface in very tiny place. If we can use something like this, it would be great. The only problem is that those guys don't handle big pressures difference between the inlet and the cold. They are not like those big pipes of steel that can, have big thickness. So why do we need high pressure? Because if we are running this closed cycle in propane, look at the pressure. That's 6 atmosphere. And the boiler is at 8 atmosphere, almost 9 atmosphere. So imagine you have like a thin plastic sheet like this. From inside, you have 9 atmosphere. And from the outside, you have the surface warm water at 1 atmosphere. I mean, the difference will just break this. So how do we do that? How do we do this? How do we do what? How we can use a very thin heat exchanger with one side propane sitting at 9 bar, and the other side the warm water that is like really it should be at atmospheric pressure, right? Or can we, if only we can get the warm water also to be at 9 bar, because the propane we are stuck. He has to boil at 9 bar. At 22 degrees C, he has to be at 9 bar, almost 9 bar, 8.7. So maybe we can play with the water. Maybe we can make the water hotter. Not the warm water hotter. The warm water is hotter. Maybe we can make the warm water having higher pressure, right? And the solution is not, let's use a pump to pump the water because that takes energy. But what can we do? Think about it. We'll continue in the second part.